Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you. Quantum leap: unlocking the future of computing. Quantum computing is a revolutionary field that combines principles of quantum mechanics with computing to solve problems that are impossible or too complex for traditional computers. At its core, quantum computing relies on quantum bits, or qubits, which are fundamentally different from the classical bits used in regular computers. While classical bits represent information as either 0 or 1, qubits can exist in a superposition, meaning they can represent both 0 and 1 simultaneously. This unique property allows quantum computers to process vast amounts of information in parallel, potentially solving problems much faster than classical systems. To understand how quantum computing works, it's important to explore a few key principles of quantum mechanics. Superposition, as mentioned earlier, is the ability of a quantum system to exist in multiple states at once. For example, imagine spinning a coin. It's neither heads nor tails until it lands. In a quantum system, the coin remains in this spinning state, representing all possibilities simultaneously, until it's measured. This allows quantum computers to explore many solutions to a problem at the same time. Another critical concept is entanglement, a phenomenon where two or more qubits become interconnected so that the state of one instantly influences the state of the other, no matter how far apart they are. This connection enables quantum computers to perform computations with unprecedented efficiency. If two qubits are entangled, measuring one qubit will immediately determine the state of the other, providing a powerful way to process and share information. Quantum computing also relies on the principle of interference, which allows certain quantum states to be amplified while others are cancelled out. By carefully designing quantum algorithms, scientists can use interference to increase the likelihood of finding the correct solution to a problem. This is a crucial advantage of quantum computers, as they can focus computational power on the most promising solutions. Unlike classical computers, which use silicon-based chips to process information, quantum computers require specialized hardware to manipulate qubits. Qubits can be made from a variety of systems, such as trapped ions, superconducting circuits, or even particles of light called photons. These systems are incredibly sensitive and must be maintained at extremely low temperatures, often close to absolute zero, to prevent outside interference that could disrupt their quantum states. Quantum computing holds immense potential for tackling complex problems that classical computers struggle with. For example, they could revolutionize fields like cryptography by breaking encryption codes that are currently considered unbreakable. In medicine, quantum computers might simulate molecular interactions to accelerate drug discovery, while in logistics, they could optimize supply chains on a scale beyond what classical algorithms can handle. While quantum computing is still in its early stages, researchers and tech companies are racing to build more powerful and stable quantum systems. The development of error correction techniques, which help maintain the accuracy of calculations despite the fragility of qubits, is a key area of focus. As scientists continue to refine the technology, the potential applications and impact of quantum computing grow ever more exciting. Building on the principles of quantum mechanics, The design and functionality of quantum computers set them apart from classical computers in significant ways. At the heart of a quantum computer is the quantum processor, which manipulates qubits to perform calculations. Unlike traditional processors that rely on binary logic gates to process information, quantum processors use quantum gates. These gates operate on qubits in ways that leverage superposition, entanglement, and interference, enabling the execution of quantum algorithms that can solve highly complex problems. One of the most famous quantum algorithms is Shor's algorithm, which can factorize large numbers exponentially faster than classical methods. This capability has profound implications for cryptography, as many encryption systems, including RSA, rely on the difficulty of factoring large numbers to secure data. If large-scale quantum computers become operational, they could break these encryption systems, potentially rendering current cybersecurity measures obsolete. This has spurred research into quantum-resistant encryption techniques, which aim to safeguard information even in a quantum computing era. Another notable algorithm is Grover's algorithm, designed for searching unsorted databases. While classical computers must search one entry at a time, Grover's algorithm leverages quantum principles to find a target item in significantly fewer steps. Though it doesn't provide exponential speedup like Shor's algorithm, it still offers a remarkable advantage in specific applications, such as data retrieval and optimization problems. Quantum computers also show promise in revolutionizing fields like chemistry and material science. Classical computers struggle to simulate complex molecules and their interactions due to the exponential growth of variables with molecular size. Quantum computers, however, can naturally represent these interactions because qubits mimic quantum states. This capability could lead to breakthroughs in understanding chemical reactions, designing new materials, and developing drugs. For instance, quantum simulations might reveal efficient ways to produce ammonia for fertilizers, a process that currently consumes vast amounts of energy globally. Despite these exciting prospects, quantum computing faces significant challenges. One of the biggest hurdles is qubit stability. Qubits are highly sensitive to their environment and can lose their quantum states through a process called decoherence. Even slight vibrations, temperature fluctuations, or electromagnetic interference can disrupt their delicate state, leading to errors in calculations. To address this, researchers are developing quantum error correction techniques, which involve encoding information redundantly across multiple qubits to detect and fix errors without destroying the quantum state. Another challenge is scalability. Building quantum computers with a large number of reliable qubits is incredibly difficult due to the complexity of controlling and isolating these systems. Current quantum computers, known as noisy intermediate-scale quantum (NISQ) devices, have limited numbers of qubits and are prone to errors. While they are valuable for research and small-scale experiments, they are not yet capable of solving problems that surpass the abilities of classical computers. The race to overcome these obstacles has spurred innovation among researchers, universities, and tech companies worldwide. Companies like IBM, Google, and Rigetti are developing superconducting qubit systems, while others like IonQ focus on trapped ion technologies. Some organizations are exploring entirely new approaches, such as topological qubits, which promise greater stability and resilience against errors. These diverse efforts highlight the potential of quantum computing while underscoring the complexity of achieving practical, Large-scale systems. The future of quantum computing holds enormous potential, with applications that could transform industries, solve long-standing scientific problems, and reshape our understanding of computational limits. However, realizing this potential requires addressing both technical and practical challenges while exploring its implications for society. In the near term, hybrid computing systems combining classical and quantum approaches are emerging as a promising solution. These systems leverage the strengths of each type of computer, with quantum processors tackling specific problems suited to their capabilities, such as optimization, simulation, and cryptography. Classical processors handle tasks where they excel, like general-purpose computing and large-scale data management. This synergy allows researchers to harness quantum computing's power without needing fully developed quantum systems, accelerating progress in fields like machine learning, artificial intelligence, and financial modeling. Quantum computing is also poised to revolutionize artificial intelligence, AI. Quantum-enhanced machine learning algorithms could process and analyze vast datasets more efficiently, enabling more accurate predictions and faster decision-making. For instance, financial institutions could use quantum computing to optimize investment portfolios, while healthcare organizations might analyze genetic data to identify personalized treatment plans. The ability to simulate and optimize complex systems has the potential to drive innovation across industries and scientific research. Quantum computers could unravel mysteries that have eluded classical approaches. From understanding the behavior of exotic materials like superconductors to modeling fundamental interactions in physics, quantum computing could provide insights into phenomena at the atomic and subatomic levels. For example, it may help identify new energy sources or develop efficient methods for carbon capture, addressing critical challenges related to climate change. As quantum computing advances, ethical and societal considerations become increasingly important. The potential to break current encryption systems raises concerns about data privacy and cybersecurity. Governments, businesses, and researchers are already exploring quantum-resistant cryptographic protocols to safeguard sensitive information. Additionally, as quantum computing capabilities expand, questions about its accessibility and potential misuse arise. Ensuring that this transformative technology benefits humanity equitably will require careful regulation and global cooperation. Education and workforce development will also play a crucial role in shaping the quantum era. As the field grows, demand for quantum scientists, engineers, and software developers will rise. Preparing future generations with the skills and knowledge needed to contribute to quantum computing is essential for fostering innovation and ensuring its widespread benefits. Universities and organizations are increasingly offering programs and tools to make quantum computing more accessible, including cloud-based quantum platforms that allow anyone with an internet connection to experiment with quantum systems. Looking ahead, the timeline for achieving large-scale, fault-tolerant quantum computers remains uncertain, but progress is accelerating. Advances in hardware, algorithms, and error correction are bringing the field closer to practical applications. Initiatives like quantum internet development, which would enable ultra-secure communication and distributed quantum computing, further illustrate the far-reaching implications of this technology. Quantum computing represents a paradigm shift in how we think about computation, blending the strange and counterintuitive principles of quantum mechanics with the practical challenges of engineering and technology. While the journey is complex, its potential rewards are immense, promising to unlock solutions to some of the world's most pressing problems and paving the way for a new era of discovery and innovation.